Hello and welcome to K Nearest Neighbor Classifier, explained for beginners. I'm your instructor Kashif Murtaza from AI Sciences, and in this video we are going to talk about K Nearest Neighbor both in terms of classification as well as in regression. But our main focus will be on classification rather than regression. And in this particular video, we are going to talk about distance, the notion of distance, because this is the notion based on which you can define the neighbors and the points that are farther away. So what do we mean by distance between 2 points in the space? And normally that is a feature space. So after defining the notion of distance, we will be able to define what do we mean by a nearest neighbor classification scheme, and then what is a K nearest neighbor classification scheme, and what is this value K in this K nearest neighbor scheme. Finally, we will extend our K nearest neighbor classification scheme towards regression, and we will see how a regressor can be achieved through the K nearest neighbor algorithm or scheme. And we will see the weighted KNN, which is a little variant of KNN, how the neighbors are utilized towards the final output. And we will wrap up our video by implementing K nearest neighbor classifier in scikit-learn in Python. If you are new to AI Sciences, just for a short introduction, at AI Sciences we deliver a lot of services related to artificial intelligence and data science. And the services include online courses, consultancies, and data science and AI, artificial intelligence developments and products, and these kind of things. Most of our focus right now on academia and research, although we are also building different apps and different products at AI Sciences also. And if you are a regular viewer of AI Sciences channel, then welcome to another exciting video on K nearest neighbors. So let's begin. Before actually starting out what is a K nearest neighbor or a nearest neighbor, it is good to first define what is a neighbor. So given, let's say, several points in space, and let's say one point of interest, in this particular case, let's say we have this particular point of interest, this point, let's say this one. So this is the point. And let's say we want to find out the distance of this point from another point, let's say this one. So x and y. One way to define the distance is just like the Euclidean distance, which is the shortest distance along the line between x and y. And that is normally known as Euclidean distance, and one very famous notion of distance that is used heavily in data science. But it turns out in several cases, the shortest distance is not the distance that is achievable, or that does not make much sense in most of the manifolds on which the data lies. For example, if you see here, although x and y, they have shorter distance along this line, and the shortest distance can be computed using a formula, Euclidean distance formula, but it is possible that the manifold or the nonlinear subspace on which this data lies, it does not allow the traveling from x to y along this path. Let's say such a path does not exist. And maybe we have another path, we have another topology of the subspace on which the data lies, and we have to, let's say, follow that topology. In that case, the distance, the shortest distance, may not be a valid distance in this topology, and we may have to come up with another kind of distance. In this particular case, these kind of distances that do not follow normally the shortest path and follow the topology of the subspace or manifold on which the data lies is sometimes known as geodesic distance. But this, I should highlight this point because I mean, the notion of distance, it varies. I mean, you need not to have, for example, although distance at the end of the day, if you have 2 points in space, let's say, distance at the end of the day is a number. that defines the distance between, so distance is a number at the end of the day. But the way you describe the distance between 2 points, that number that eventually is called distance, may vary depending upon the data set and the constraints on the data you have at the end of the day. And that's precisely the reason if you see a lot of packages in Python and in other data science languages and packages, you have a lot of distance matrix or distance measures that are available. And maybe depending upon the data, one distance measure works better than the other on a given data set. So I felt it essential to describe distance at the end of the day is a number between 2 points, but the way you define distance may vary, and what distance measure to choose is again a hyperparameter depending upon the task and data at hand. In this video, we will mostly talk about Euclidean distance, but feel free to choose the distance measure through cross-validation or validation on your data set. That may work very well. And this is the distance that eventually defines the notion of neighbor. What do we mean by a neighbor? Consider, for example, this particular point. And let's say you have set some distance metric. In this case, let's say we have set the Euclidean distance, the shortest distance between 2 points. Maybe I want to find out the distance of this point to several other points, all different points. Then the nearest neighbor of this point is the one that has shortest distance with this particular point. So for example, in this particular case, this one is the nearest neighbor of this star point. And here in this particular case, for example, if this is our point and we want to find out the nearest neighbor, then the way to find out the nearest neighbor is to compute the distance of this point to all the available data points and find out the one which is closest to it, and that is what the nearest neighbor. And the nearest neighbor classification scheme is nothing but finding out, for example, for a new test point, find out the nearest neighbor, the point which is closest to the new test point, and see for that closest point what is the class label of that closest point is. If the class label is, let's say, 0, then your test point belongs to whatever its nearest neighbor belongs to. And if y is equal to 1, so the nearest neighbor classification scheme works like the following. You have a new point comes in, you find out the distance of that point from all the points and find out the nearest neighbor, the point that is closest to that particular point. And see what is the label and what is the class of the nearest neighbor. Whatever the class of the nearest neighbor is, that is the class of the test point. And this is known as nearest neighbor classification. It turns out that nearest neighbor classification has a jittery boundary, and it is very, very sensitive to noise. So to remove that, one way is to, rather than focus on just one neighbor, let's focus on k neighbors, where k is a number which can be 1, 2, 3, or maybe n minus 1, where n is the number of data points. So based on just one neighbor, if we decide the classification label, then that is called the nearest neighbor that we have seen earlier. If we, for example, pick, rather than one neighbor, we pick 2 neighbors or 3 neighbors, the best 3 points, the best 3 neighbors or 4 neighbors or 5 neighbors, and then we pick the label out of the majority vote of the nearest neighbors, the k nearest neighbors, then that particular scheme is known as k nearest neighbor. So it's very simple to nearest neighbor, but rather than just one neighbor, we are now getting the votes from more than one neighbors, and that more than one neighbors is the value k, which is the hyperparameter. By hyperparameter, I mean there is no fixed rule to find out this particular value of k, although there are rules of thumb and there are heuristics to find that out, but mostly this is set and this is found using cross-validation on the given data. So let's take an example. Let's say we have this test point, new point comes in, and let's say our value of k here, is 7. Let's say we are working on 7 nearest neighbor. So what we do is we compute the distance of this point from all the points on the training data, all the points, And then we find out the 7 points that are the nearest neighbor of this data point. And when we compute the distance of all the points, we compute the distance of all the points from all the classes. And then we pick the 7 nearest neighbor regardless of their class label. In this particular case, the 7 nearest neighbors, they turn out to be this one, that one, that one, that one, and that one, and this one, and that one. Out of these 7, we will then get the majority vote. Which class is in majority? In this particular case, class B is in majority because out of the neighbors, there are 3 votes for class B, 2 votes or 2 members of class A, and 2 members of class C. So in this case, due to the majority voting, class B wins. So the label of the new test point happens to be class B. The situation may become different if, for example, the new test point is here. If this is the new test point and we compute the K nearest neighbors and the 7 neighbors, in this case, all the 7 neighbors, they will be from class A, and the class A clearly wins. But there are boundaries in which the vote can be distributed among different classes, and we take the majority vote out of it. What should be the best value of K? Well, if K is too small, the classification scheme is much sensitive to noise. If K is too large, then it is computationally expensive, as well as the local structure and the local neighborhood information goes away. So one rule of thumb is to take the value of K as square root of n, where n is the total number of data points collectively in all the classes. That's one rule of thumb, although one may have a different value of K working on a specific data set, maybe very well than n square root, but well, that's the rule of thumb or heuristic most practitioners use if nothing else is available. So that's the K nearest neighbor classifier. Very simple, very powerful, and it's used a lot in direct classification. It is used as a pre-processing step in dimensionality reduction. It is used to find out the neighborhood graph for semi-definite embeddings or the manifold kind of dimensionality reduction. In the nonlinear dimensionality reduction, most of the cases people build these K nearest neighbor graphs and find out the geodesic distances and that kind of stuff. So the applications of K nearest neighbors are a lot. One application is just the direct classification, which indeed is also very powerful. How can we use this particular scheme, which means finding out the K neighbors, and then rather than getting the vote, how can we extend this scheme for regression? So for example, let's say we have x1 and the corresponding value is y1, then we have x2, then the corresponding value is y2, and let's say we have a lot of data points, xn, and the corresponding value is yn. And assume all these targets, they are continuous valued rather than discrete valued. So so that might be a regression problem. And also these x1, x2, they are feature vectors, maybe lying in a very high dimensional space. So how can we extend, and let's set the value of K, let's say is 3. And let's say a new data point comes in, let's say xt that appears, and we want to find out the corresponding y value for xt in the regression setting, where K is, let's say, is 3. How can we extend our K nearest neighbor algorithm for regression? Well, one way is to compute again the 3 best neighbors, 3 nearest neighbors of xt. Let's say they happen to be, just for example, let's say the nearest neighbors are, let's say x7, x31, and let's say 52. Let's say these are the neighbors of xt with the corresponding y values as y7, and the corresponding y value is y31, and the corresponding y value here is y52. Then the y value for xt, one way is to find out the y value is just to average these values, just add them up, all the values, and divide by 3, and you get the average value, which is the yt hat. So this is one way of extending the K nearest neighbor classification scheme or the K nearest neighbor technique for regression. Finally, we talk about weighted KNN. So far, what we have seen is that if you have K neighbors, let's say, for example, k is equal to 3, and let's say you have 3 neighbors, x, let's say 7, x 31, and x 52. Let's say you have 3 neighbors of this particular point, and they have their outputs, let's say y7, y31, and y52. Then what you're doing, whether you are doing classification or regression, what you're doing is you're giving the same weight to all the outputs. In regression, you are doing the averaging or uniform averaging, and in case of classification, you are doing the uniform voting. What weighted KNN says is that the neighbors that are more closer to you, they should get a higher weight. They should contribute more in voting or in averaging, depending upon classification or regression. So in that case, not only the identification of neighbors matter, but also this matters which neighbor is how far away from the actual data point. We again pick the best neighbors, let's say 7 of them or 3 of them, whatever the value of k we set. But out of those neighbors, we do not treat all of them uniformly, but we treat them, some of them are more important than the other ones, depending upon how closer they are to the test point. And several such techniques exist for weighting the final outputs in KNN. So that's a quick and I mean, maybe it's a very quick overview of KNN. Let's now go to Python and see how can we implement this on, let's say, built-in dataset, Irish dataset. So first, let's import some libraries like from scikit-learn. Let's import K Nearest Neighbors, and let's import that as K Nearest Neighbor Classifier. Then for training and test split, let's import this library. Let's import train test split. For visualization of the results, let's import confusion matrix. For a better visualization, let's import Seaborn and NumPy for array processing, and for plotting, let's say matplotlib .pyplot, and that's the environment for plotting that we set here. The example data that we are taking for this KNN tutorial is again iris data. Iris data has 4 attributes and one class attribute, and total 3 classes. So if we see the total number of classes here, the total number of classes here are 3: Setosa, Versicolor, and Virginica. So let's prepare the data and pick the real attributes out. And let's split the data into train and test data, where 80% is used for training and 20% is used for testing or evaluation. Let's call the K Nearest Neighbor Classifier with the total neighbors, or the value of k. This is the value of k. N neighbors is the value of k. The default value in scikit-learn is also 5, but you can change that value by specifying a number here. Remember, too small value is bad, too large value is bad, and maybe the best value can be found through cross-validation. So let's fit the model, and let's predict the test points, and let's evaluate, or let's visualize the results of, or the performance of our classifier. So the performance is really good. All the Setosas, they're classified as Setosas. All the versicolars, most of them, they are classified as versicolor, although one of them is classified as Virginica. And similarly, all the Virginicas, most of the Virginicas, they are classified as Virginicas, but the one that actually is misclassified as versicolor. So that's the quick implementation of K Nearest Neighbor Classifier in Python. I hope you have enjoyed this video. Please subscribe our channel, like this video, share this video to your friends, and in the description, see the more and more resources that are available there at AI Sciences. Hope to see you next time.